Anyway, so I'm going to start recording, and we're going to do a little bit of Q&A, but also kind of review something. So there's one topic that I did not get to with you guys that I think is kind of important. I'm trying very, very hard not to load you guys up with more homework than what you can handle, because I know that with an hour of instructional minutes missing from every period of every class that you have, a lot of our teachers are like adding some of that onto you to try to make up for that lack of time. I want you to know that I'm not doing that. I'm actually deleting a lot of stuff that we do, but the downside is when I delete, it means you don't have as much practice. So pros and cons, right? So if you're like, you know, like and I know that that's hard to relate to at your station in life, but there are people that will actually come and say, hey, can I have some more homework? And I know that's like baffling to some of you to hear, but when somebody's like, you know, I really want to understand this and I'm struggling, can you show me a couple more that I could practice with and give me an answer key so I can make sure? I have a lot that I'm not giving you because of just time. So if you need more practice, that's would only help your grade, because if that's what you need, just let me know, because I'm going quickly. But I'm doing some of that where I'm taking what used to be 3 assignments and try to cut them down to 2 assignments, because I'm trying not to load you guys up with that extra hour of homework. So I'm trying, but if it's too fast and you need a little bit more practice, just let me know. Okay, so I have the set, and you've seen something like this before. I know you have. Let's see, if I turn the light on, does that make it it did a little bit better, didn't it? So can you guys look up there and let's talk about what we know. This represents a polynomial. I know you've seen one of these before, at least a couple of times. Can you guys tell me anything that you know about this polynomial? And if it helps, I'm going to go ahead and I'll draw this in right here and right here. I'm just trying really hard not to accidentally hit those top numbers too much. But this was the question and some divisors. Tell me something that you know about my polynomial. No.
There's a root at 3.
There's a root at 3. That is a fantastic thing to note. So if there is a root at 3, then we know we have a factor of x minus 3. Okay. In fact, underneath here, tell you what I'm going to do. I'm going to write x minus 3 times something, because I kind of like this line right here. So what degree polynomial is left now that you took that x minus 3 out? Can you tell? Let's count it up. This would be the constant, wouldn't it? That would be the x's, the x squareds. What is this? It's a 4th degree now. So originally it was a 5th degree, right? So this is 2x to the 4th. Let me see if I could find it. Plus an x to the 3rd, minus 25x squared, minus 2x plus 42. You guys all right with that? It was a 5th degree when it started. Well, let's count it. This would be the x to the zeros. This is x to the 1st, 2nd, 3rd, 4th, 5th. Okay. What else do we know? So it started out as a 5th degree. But by the way, I love taking that because that cut it down at least 1. Okay. What else do you guys see? So this is one of the ones that you were asking about. Let's see if you could help me with those bounds. Go ahead. No, that's fine. There's one between -1 and 2. Now, why do you guys know that there is a root right in here between -1 and -2? Switches signs, doesn't it? Now, I'm going to try to use the vocabulary to be very careful here. That's actually in mathematics. Listen to this carefully. It's called the intermediate value theorem. What does intermediate mean? It's kind of like in the middle. What is in the middle of negatives and positives? 0. We call it the intermediate value theorem. So it sounds fancy, but it just means if you went from negative to positive or vice versa, you had to go through 0 on the way, didn't you? Okay, you guys see? So I think there's one in here. You said was between -2 and -1, right? Okay, what else? There's also one between 1 and 2. Oh, right here, similar rationale, right? Went from negative to positive, okay. there anything else you see? There's one more. What's that? Okay, that's the one that I was actually hoping that we would see. Okay. So how many roots does this thing have? Man, 1, 2, 3. It looks like we already see 4 of them, don't we? How many roots can it have? 5. Okay. Let's talk about bounds. What bounds do we have? Yeah.
There's the greatest lowest bound at
I love it.
-2. I don't know if it's the greatest one, but
Plus, minus,
the one above it.
plus, minus, plus, plus,
Oh,
plus, minus, plus, minus, plus. Ooh,
there we go.
did that one work? So what do we call that? The GLB. Very nice. That was the greatest lower bound. Now, what I'm trying to get at with you guys, do you guys notice what we're doing? We're analyzing, aren't we? What's the name of the class? Math analysis. What I'm trying to do is like, how do we actually work smart? Okay? Let's just sit back and kind of talk about it. It's almost like math meets philosophy. Like, what do we do to kind of like, before we, do you guys have an upper bound then for me? I heard somebody say 6, 2, 7, 14. What do you see about all these coefficients? Positive. How about 5? Dang it. Close, but no. All right. So, Theorem. What does that mean then? What do those highlights mean that I put a highlighter at -4 and +6? Why did I highlight them? You don't know. Mr. Sanders, why did I highlight those? What are we looking for, everybody? Roots. Why did I highlight those? The roots are in there. That's it. So would we even bother to look at 9 or 10 or 12 or anything out here or up here? What this is this is bounds. Don't even bother to look above that or below that because it has to be in there no matter what. Whether they're pretty or whether they're ugly, they're in there. Does that help a little bit in our search? It's sort of like playing hide and seek as a kid. You're like, I don't know where to look. Well, the first hint is they're inside the house. Okay, well, we just remove the yard, right? What did we just remove? We removed every number above 6 and every number below -4. Did that help in the search a little bit? Should be, right? Okay, now, can you guys help me come up with a list of possible rationals? Because that is something I definitely want you guys to be able to do. Now, I'm not going to go up to this original problem because Noe helped me out by noticing that that 3 was there. And so instead of factoring the big sucker, I'm going to factor this slightly smaller one. So where do we start with the possible rational roots theorem? Which number do we start with? The last one, which is the number 42. So what are the numbers that divide beautifully into the number 42? 1, 2, does 3 work? Yeah, it does. Dang it. Does 4 work? No, 5 doesn't, 6 does, though, and 7, 14. By the way, that does not make me smile. That's way too many options, isn't it? That's what I hope doesn't happen when I'm doing one of these big problems. And then my leading coefficient is here. But let's go to the easiest one that I see. Way up here, one of you guys saw that there was a root between -3 and -4. Can you find a fraction in that whole shooting match that's between -3 and -4? -7/2. Does that work? Is that over here, 7/2? Oh, I forgot my plus or minus. Now, by the way, when you said 7/2, I want to make sure that you guys remember that. What's the big deal about writing it this way? Who remembers the special trick? We're going to have to divide by 2 at the end, right? Because we're not supposed to do that. So let's see if we can hang with this one. We're going to write -7/2. Now, if this is successful, what degree will be left? We went from a 5, no way found one, we're down to a 4. If this one works, we're down to a 3. If we can find one more, what are we down to? A quadratic, and that, ladies and gentlemen, is the one we want, because we know how to solve those. Okay, so what's going to happen when we do synthetic division? What do we do first? Bring down the 2. That's going to multiply, gives me -7. Ooh, 42 over 2 is 21. Bring down the 4. Got to be careful here. That'd be -28 over 2, which is -14. That was terrible. Did I mess that up? I know I did. That'd be +28 over 2, which is +14, which should make this a 12. And 7 times 12 is 84, divided by 2 is 42. And is that a positive or a -42? That's a well, that's a positive times a negative. That's negative. Now, the nice thing is we just said, remember, that we're going to divide them all by 2 because of that picky little sucker right there. So did our problem just get better? Now, honestly, at this moment, I honestly personally got a little bit stuck, although I kind of knew what the answer was. So would it hurt to peek at the graph? And when I peeked at the graph, I saw a little parabola sitting at 3. What would that tell you? What would that tell you if you saw a little bounce at the number 3 on the graph? That it's a square. So not only did 3 work once when I divided it, it's going to work another time. So let's see what happens if we now divide by 3. What just happened, everybody? Did it work? And what does that represent? This is what I really want to make sure you guys get. What does all of that represent? What is this? Okay, we had started with a 5th. We took out the 3. Then we took out the 7/2. Then we took out the 3 again. What's left? A quadratic. So what does that 1 stand for? 1x squared. There's no x's and a -2, right? So what we just did is we took this whole thing and we found x minus 3 happened twice, didn't it? We found out that the 2x plus 7 happened. And then we had this. So what are my roots? 3 with multiplicity, 2, bouncy. What happened here? Little line there, and then, ooh, x squared minus 2. What are the roots of that? Root 2 and minus root 2. Those are the 2 roots that were in here that we weren't really able to see. They were this one right in here and this one right in here. This is what I didn't get to with you guys last time, and that I wish I had. What if I said, okay, yeah, graph it? How do we graph it? So here's what I want to do. What's the highest root that this problem has? This is something I do want you to be able to execute. The highest root on this thing is 3, isn't it? And the lowest root is -3.5. So here's what I would do. Is I'm going to take out a nice big fat piece of graph paper. And I'm going to go 1, 2. Why am I counting by big numbers? Why am I spreading it out that much? Because what's the thing going to do after it leaves that last root? It shoots up to infinity or goes to -infinity, doesn't it? Hello? Sure. No way, they need you at the office. All right, let's go to -1, -2, -3. Now, could you guys handle this like actually doing this right now? Where are the roots now? This is gonna, by the way, we're almost done with this problem, I promise. I know I had one at 3, right? I had one at -3.5 out here. I had one at plus and minus root 2, which is about 1.414 here and here. Now, what degree was the polynomial? 5th degree. How does a 5th degree have to end? It has to be up over here and it has to be down over here, doesn't it? Now, we know we needed a bounce right in here, didn't we? Here is where I really need to make sure we finish it up because this is the thing that I didn't do with you. Nothing has changed yet. I want a couple of points in here to tighten it up. You mean more work? Not really. What would be a nice point in here that you could plot that would help see how high or how low it goes? The y-intercept. Oh, in other words, what would happen if we plugged in 0? I got negative 126. Keep that in the back of your head. See, aren't all of these coordinates? So if you just needed a couple of coordinates, how many did I give you? I gave you 15 of them. We're not going to use all 15. We just want a couple. So I know 0 giving me negative 126 is pretty good. What's another one that would be helpful to plot if I was going to try to do a good job of this? You think 2 would be good? Let's find out that one. When I look over here at 2, what's the height at 2? Just like 22. And then one more. That's all I want. Out of the 15 coordinates I gave you, I only want one more. What should we pick out here? Negative 2? By the way, now I love the fact that you said negative 2.5. And I could go get that, but I'd have to earn it. So what about if I just told you negative 2 itself? Would that be close enough? By the way, if you do negative 2, I'm not going to do that. It's at 150. Now, the reason I do that first is that going to help me establish a scale to count by. Should I count by ones on my graph paper? I don't think I want to do that. What should I count by if I'm going to go up to 150? 20s? 30s? I was just going to go by 10s. I got a lot of space here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's 100. 10, 20, 30, 40, 50. There's 150. So at 0, I got negative 126. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 26. See, there I am. At 2, we're at 22. That's kind of weird. It didn't go up very high, did it? Why didn't it go up very high? Not a lot of space in here, so I know it does something out like that, doesn't it? This one's going to pop way the heck down here like this, and then it's going to come back up. And then how about between negative 2 and negative 3 is it went all the way up to 150. And I'm really actually very thankful that nobody asked for the other number. Because if you tried negative 3, it's actually at positive 250, and then the scales are even harder to deal with. So good enough for me. But anyway, does this actually now give you an extremely strong view of what the graph actually looks like? Now, all I did is I added what? All I added was this, this, and this. Did you have to work hard to get those points? I handed them to you, didn't I? So that's what analysis for me is like, can you look at it and tell me about it without doing a truckload of work? Now, could you do that other work if you needed to? Yes, but I don't think we want to take that time, okay? So, do you guys have any questions before we move on to today's stuff? I think you guys are going to maybe kind of like today's. It's kind of cool, kind of weird. We're going to start talking about imaginary solutions. So, before we do that, I'm going to tell you a little bit of a story. 2, 3, 4. 1, 2, 3, 4. 1. Okay, so you guys that are online, they're really, the notes just kind of help me out, but really they're not a huge amount of stuff to write down. So I didn't really think it was probably worthwhile to do that. But let me take you back in time to something. There was a book that, have you ever had a math teacher make you read a novel? I've only had it once before until college. I had a couple of them that would have that. But there was this teacher in high school, my geometry class, and they made us read a book called Flatland. Now, flatland is weird, but it was a land that was flat. And his idea was, the author's idea, that flat land was literally a two-dimensional land. So it means like you lived on the whiteboard or on the floor, and everything that you could do is move left and right, or, you know, up and down. But there was literally no concept of a third dimension, which was up or down. You with me on that? So what he was trying to do, the author, is he was trying to show you how sometimes our perception can be very, very flawed. Is there such a thing as a third dimension? But if you lived your entire life without that other dimension, would that change your world a lot? And in fact, like, imagine somebody that is blind, they cannot see, and all of a sudden they can. Would that really just completely blow like how you sense everything? It would just change everything. Like, how can somebody describe how something looks to you if they've never seen, right? Well, that's kind of the idea behind it. It was very controversial at the time because it was a geometry thing. So guess what all the characters were? They were shapes. So a triangle was a very lowly person. A square was a little bit more powerful. Better than a standard quadrilateral, but you know. And then what was the most powerful one in the whole story, in the universe? And this, what would be the most powerful? The most sides, the circle. The girls were very, very mad at my teacher for assigning this book because he made all the girls line segments. That was kind of rude, wasn't it? Now, my teacher didn't make them line segments. The author made them line segments. And it was mean. But there was a reason behind it, because he was trying to teach people about dimensionality. So if you could imagine, if I stand back here like this, if I held my pen this way at you, and my pen was a line segment, a literal line segment, what's the problem? You won't see it. Because a line segment has absolutely no dimension. If you look at it this way, it was infinitely thin, which meant women would well, they were dangerous because they could kill people because they couldn't even see them. They could sneak up and stab people, you know? I mean, it was kind of silly, but he was trying to like say, like, when we think about things, it's really, really complicated. But he couldn't describe to people what this thing was up because the character came into contact with something from the third dimension, and he was trying to describe it to everybody, and they thought he was crazy. Does that make sense? Like, if you're trying, like, you experience something brand new no one has ever seen before, they think you're nuts, right? Well, guess what? This is the story. All the way through elementary school, you guys, all the way, in fact, even through Algebra 1 and halfway through Algebra 2, you guys lived in flatland. You did. You had never dealt with complex numbers before. You had never heard of I, correct? You'd never heard of that. So here's the kind of the interesting thing. If you wanted to graph 2 plus 3i, you know what that is? That's 2 plus 3i. This is a little thing that I was going to assign early in our course, and I cut it out because I didn't want to take the time at that moment. Where would negative 1 plus I be? Negative 1 plus I would be, I mean, you've done that before, haven't you? This is another visual way of doing it. But in elementary school, and they said, hey, where's 4? You'd be right there. What did you not do? You never went up, right? You were in flatland. Was this technically a number that is complex? Did it have an imaginary component? The answer technically is yes, but what was it? It was 0. So this is what I really wanted to get at you guys. Every number you have ever seen is a complex number. Do you know that? But what do we use? 0. We need to now make sure we can look up. Are these still going to be good numbers that don't have an imaginary component? Yes, but technically they're all considered complex. And any complex number, please do write this down, looks like a plus bi. So a plus bi, a is the real part, B is the imaginary part that would either go up or down in the complex plane. So sorry about that. That's just kind of a weird little lead-in that I had to go through. So if you have a polynomial that is of degree n, then oh my goodness, it has exactly n complex zeros. So if I give you a third degree polynomial, what am I telling you? It has 3 complex roots. If you had a fourth degree, what does it have? 4 complex roots. Now, the reality is, are some of those complex roots ones like this where there was no imaginary component? Yeah. So we're going to put right here both real and imaginary. Now, there's a much more technical way to say that, but I'm just wanting you to know that sometimes it's all perfectly real, that B part is 0, and sometimes it's not. So when we go a little bit further, there's a theorem, which means it can be proven, but I don't want to take the time to do that, is if you have a polynomial that has real coefficients, that you're going to see that today. We're going to have some imaginary roots, but the coefficients will be real. If A and B are real numbers, so A plus BI is a 0, then its conjugate, you guys heard the term conjugate, I'm pretty sure, is also a root. And so if A plus BI is a 0, then A minus BI is also a 0. So this is pretty big. So if I give you one of the roots, what am I automatically giving you in reality? 2 of the roots. So not that I'm going to go there just yet, but we'll make up a deal about it in a second. So when we hit number 6, I'm going to tell you that 3 minus I is a root. Then what am I automatically telling you right now? 3 plus I is also a root. So in this third degree polynomial, how many roots are there? 3. How many of them did I already give you when we started the problem? 2 out of the 3, you're just going to find the third one, okay? No big deal. So we're going to cheat a little bit. So let's go through a little something. This is review. Remember, if we have a polynomial with a root of 2/3, it has a factor of 3x minus 2. I'm going to remind you something, and then I want you to try one on your own in a second. What is the factor that would go with -4? X plus 4. And then x minus 1. Now, this is called a product of linear factors. Do you guys see that? Those are all linear factors, because doesn't that look like a line? Slope 3, intercept 2. Does that look like a line? So this is a product of linear factors. But we're going to go ahead and go, sorry, standard. So keep in mind, when you multiply things out to get them into standard form, you're just going to multiply 2 at a time. I knew I could do these pretty quick together, so I just did that. And so I got a 3x cubed. Let's see, how many x squareds are there? There's 9 here and minus 2 there. How many total? 7 of them. How many x's are in this thing? I think I got a -12 there and a -6 there. -18. And then my last deal was 8. Now for the test that's coming up, right after Thanksgiving, right after turkey time, what would you do to make sure that you did not multiply that out wrong? Could you graph this and graph this, and what should you see? You should see one graph. If you look at the table, should they all have the same numbers in the table? Please do that, because it's so easy to make a mistake. Now, the reason I asked you that question is because of this one right here. This is kind of a booger. This is mine, this one's yours. So notice when I said the root was -4, you wrote a +4, right? And when the root was a 1, you wrote an x minus 1. So in other words, whatever the root is, you take it away, don't you? So watch what happens. I've got this complex root. Notice the conjugates, everybody? 2 plus 3i, 2 minus 3i. So I'm going to take these roots away. There's x minus the first root and x minus the second root. Watch it carefully. When I subtracted each of those roots, that's what happened. See, I took away 2 plus 3i, and I took away 2 minus 3i. Shoot. Well, one of the guarantees that I made you is when I do it all, I'm going to have real coefficients. So what has to go away when I'm done with all this stuff? All the i's have to go away. They will, guaranteed. So let's go through the process. I'm going to distribute x by all three. And it looks like I lied because I just saw an imaginary number, didn't I? So notice I distributed the x by all three. Now what should we distribute? We did the x. What should we do now? Should we do the minus 2 by all three? That would be a minus 2x, a plus 4, and a minus 6i. So that was the first three. This was the second set of three. And now we got our third set of three. Okay, cool. All right. What the heck? I said there would not be any imaginary numbers. What do you need? Do you notice anything happen? What's that? I squared is what? I squared is what? Thank you. I squared is a negative 1. Oh, that's helpful. So what is this negative 9i squared sitting right here? That's 9. That's cool. Okay. Keep that in the back of our head for a second. But there's something even easier. What else do you notice? What cancels? Where? I got a negative 3ix right here and a positive 3ix right there. What else do you guys see? A negative 6i and a positive 6i right there. Those went away too. Now, the temptation is people are like, well, if they're going to cancel out, can I just not do them? Because I know they're going to go away. Well, you want to be careful that you don't miss somebody. So when I put it all together, I got x squared. How many x's do we have? Minus 4x. And then there's a 4 there. And what did you say about this one right here? It was a positive 9 for a total of 13. Oh. So guess what would happen, everybody, if you did the quadratic formula on this problem right here? You would get those two roots. So did we get a quadratic? Second degree, 2 roots, no imaginary coefficients? We're good. Your turn. Ooh. See if you guys can do that one. Yes. 13. Oh, how do I get 13? Because there's 4 right here, and this is actually a positive 9. Because the I squared is negative 1. Now, Kevin and Sabrina, there is something that we're going to see very soon that is a shortcut in these problems that is going to make your time watching this be very, very worthwhile. I'm making you guys do the long one first, but then I'm going to show you a cool little trick. quadratic, save time. The quadratic you should have had was x squared minus 14x plus 53. I see a couple of you guys shaking your head. You're like, you're good to go. Okay, good. And then we do some work on that, you know. By the way, would you guys like to be able to just write that down just by looking at the question instead of doing all that work you did? Would you guys like me to tell you a trick where you can literally look at that problem and write that down without actually multiplying it out? Be a nice trick, wouldn't it? I'm going to show you that trick. It's pretty cool. Okay, so you got x cubed, right? How many x squared did you guys get? Negative 12 of them? Yep. Now what? How many x's? 25 of them? I like it. And 106, right? By the way, if you graph this, how many places would it cross the x-axis? Not 3. 1. Why only 1? Because the other 2 roots are imaginary, and you're not going to see it. So when I was teaching in Southern California, I was at Downey High. There was this old teacher, Mr. Hodges, came in, and I was kind of going over this with some of my students, and he's like, huh, you don't know the trick. And I'm like, what trick? He goes, oh, this is a really, really cool trick. He said, oh, all you do is take those two, see those 2 roots right there? What would happen if I just added 7 plus 2i and 7 minus 2i together? What would you get? What is 7 plus 2i and 7 plus 2i added together? Isn't that just 14 because the i's would go away? Does that always work? Let's go back to this one. What is 2 plus 3i and 2 minus 3i added together? 4. That's kind of interesting, isn't it? Now here's the other part that's kind of weird. What's 2 squared? 9. What's 3 squared? Sorry, 2 squared is 4 and 3 squared is 9, right? What's 4 and 9? Let's see this one. 7 and 7 is 14. So I went negative 14. And what's 7 squared? 49. And what's 2 squared? 49 and 4 makes... Does that always work? Turns out it does. Now, if that teacher didn't tell me why it worked, I'm a why guy. I want to know, if you're going to tell me hocus pocus, where does it come from? Well, the silly thing is if you write it this way, because that's what we're doing. We take x and we subtract a root. We take x and we subtract the other root. When you start multiplying it out, this is what happens. And I know this is a little complicated, but there's a really nice little payoff that's right here. Look at this chunk of the story right here. By the way, I just did distributive property on x minus r1 and x minus r2. Sorry if that's a little bit small. Let's see, is that better, Olivia? Okay. Guys, what do those 2 things have in common? Look at it. What are those yellow pieces that I highlighted? What do they both have in common? They both have an x in them, don't they? What else do they both have? A negative. So if I wanted to, I could write it this way. Now, what did I just tell you to do? Didn't I just say add the 2 roots together? And then I just put a minus in front of it? And then this is the goofy part. Since one of them is a plus bi and the other one is a minus bi, when you start distributing that, you'd get a squared. Look at the outer, negative ABI. What's the inner? Positive ABI. What happened to those things? What is ABI minus ABI? Cancels out, and then BI times negative BI is negative BI, geez Louise, negative B squared I squared. That's so hard to say. But what was I squared, everybody? Negative 1. What is negative 1 times negative B squared? Okay, now I just did the hard stuff. Now let's do it the easy way. This is why this trick that he taught me works. It's so ridiculous. So if 6 minus I is a root, then what's another root? 6 plus I. So, guys, what would happen if you took those two roots and added them together as they stand right now? You get 12, so I write minus 12x. What happens if I take the two coefficients at play and I square them? I'd get a 36 and a 1. There we go. What do you guys think? Is that pretty slick? You can literally look at it and do it. So x squared, what would be next? What happens if you add them together? 8. So what am I going to write? Minus 8x plus, and it's always a plus, by the way. 16 and 25 makes 41, and I'm out. Did that save me a little bit of time? Okay, do the last 3. Okay? You do those 3. See if you guys can all handle the trick. Real quick, let me do a quick stop share because no, Kevin, yeah, there wasn't a lot on this. They're just little things for me to help me follow a little bit. So the packet I didn't put up. I actually did put the homework and stuff in there, but I didn't actually put the packet in there. My apologies about that. I can share that, but I thought writing 6 minus I was just easier for you to write both of them out. So I did not actually print that. All right, let's see what we got. Amazing. X, what's the first one? Okay, x squared, I like your 16x. But it's a minus. Whatever you get, you always change it because it right here, remember we factored that minus out. And then, Caitlin, can you tell me what the last number is going to be? 80. Nice. 8 squared is 64. 4 squared is 16. That's going to make 80. I like it. I like it. I like it. I like it. Gabe, can you do the next one? X squared what? Ooh, why did you go plus 10x on that one? Because it was a negative already. I added up, I got negative 10, so it's a positive 10 plus what? 34. 34. All right. Hiram, I want to see if you can redeem yourself. You had to say no before, so can you do this one? You don't think so? I have faith in you, man. You want to phone a friend? Okay. Who's your friend? Royce? Minus 24x. I like it. 145. Royce, can you tell Hiram what you did? Yep, you added them together. The constant part made 24, so we just did the opposite. And then the 145, what'd you do? Square both and add together. We're done. Isn't that nice? You guys like that? All right. Now, there's a little something, there was a typo, and so I fixed it. Not in a very elegant way. That's my elegant fix. So Kevin, this is actually why I didn't bother, because most of this is just writing something down like that, and I thought it was probably not worth you guys printing it out with so little information on it. So every year, this comes up in our textbook as well as other people's notes and stuff like that. And people go, write it as a product. Now, what does the word product say? Like it's some kind of a multiplication question, right? Of linear. What does a line look like? Isn't a line like mx plus b? Can you tell me the line that would produce the root 2/5? 5x minus 2. Is this a linear factor? But it says linear and irreducible quadratic factor. That's funky. What's a quadratic? All those things we were just doing were quadratics because they had x squareds in it, didn't they? So if 2 minus I, then 2 plus I. Olivia, what is 2 minus I and 2 plus I going to give me then? Better be minus 4x, right? Because remember, we added them together, we have to change that sign. And how about the constant at the bitter end? 5. Now, let's break this down. Is this a quadratic factor? What the heck is this irreducible thing? Can you factor this, everybody? Can you come up with two numbers whose product is 5 that add up to -4? It sounds good, doesn't it? Oh, it doesn't work, does it? No matter what you do, it doesn't work. So what is this thing? This is called an irreducible quadratic factor. So what am I saying is, could you just stop there and call it a day? Is this a good polynomial that has these 3 roots? Can you guys do this one for me then? Do this one. Now keep in mind, you're going to make the set of linear and irreducible quadratic factors. Kaylee, what degree is this polynomial? Thank you. 5. Perfect. I only gave you 3 though, didn't I? Why'd you know it's 5? Because those extra ones, those conjugates, right? Okay. Cameron, can you tell me one of the factors? 4x plus 3, that would be called a linear factor, right? You took the easy one. I like it. Thomas, can you give me another one? Isn't that obnoxious? But you can look at it and see it. You got the last one? You don't like that? That looks a little scary, doesn't it? Because like that real part is missing. Because so Jacob, you think you got it? Okay, what do you think? Yes. You probably had that. It's x squared plus 9. What happens when you add them together? You get 0, so you don't have any x term. And then when you square the 0 and the square of the 3, you get 0 and 9, which is 9. Hey, so what do we have? Break it down for the test. Would that be mean if I asked you to write in linear an irreducible quadratic form. By the way, if I do that, I'm being nice. What's the mean thing to ask for? If I ask you for standard, you're like, you suck. You're going to make me multiply all that out. Wouldn't that be terrible? But we can do this. Here's the only downside. This is a trick, isn't it? See this thing right here? Thomas got it down really, really well. A lot of you guys have it down really, really well. Here's what I see every year. I have a handful of people come in and go, oh, there's a trick. I can't remember it. Make sure you look over that, you know, and don't forget it because it is a trick. Doesn't it feel like a trick? It's not. It's not a trick, ladies. I'll even call it a trick, but did I show you where the trick comes from right in here? I showed you, it's not a trick. It's like it has to work. Now, here's the last part, and this is where we're going to finish up. Now, I'm going to do this in a little bit of a different way. So if you do not have a graphing calculator, you're going to need one in a moment. But for the sake of time, I've told you we lose an hour, so I'm going to try to go quickly through one of these things, but we'll see how this goes. Okay, you see how 3 minus I is a root? Then what better be a root? 3 plus I. Okay, so this says let's find all the roots, and I'm asking, is that one a root? Well, if it is, then so is 3 plus I, right? Well, if those are both roots, now keep in mind, let's imagine I gave you the number 1,280, and I said, is 2 a factor and is 5 a factor? What would happen if I just divided by 10? Would that establish that 2 work and 5 work if I divided by 10? Because what is 10? It's both of those things put together. So if this works, does that have to work? And if they both work, that means this has to be the quadratic factor that would divide. So if I divide by that, what am I dividing by? Both of them simultaneously. You follow me? That would be doing like a quick 2 for 1. So the question is, did that 2 for 1 actually work? That's what they're asking. Now, it says, is this a root? Verify this is a root. If I do that, I've done both of those questions, haven't I? So what would it take to make x cubed pop out of this thing? What do we need? X. So that's going to be x cubed. So hell, what's the next thing that happens after we do that? This is the next step that sometimes people forget. After we've come up with what that is, we multiply it. What's the next step? Subtract. Yes. We're going to change all these signs. And then we bring it on down. What's the bring down? That's x squared. Do we notice anything nice? What happened? What's the magic number that has to go out here to make it work? Oh, 1. Hey, did it work? Did it divide perfectly? I mean, we could show the steps, but, you know, honestly, sometimes we give up on that. So the question was, find all the roots. So what are all the roots? Oh, careful, careful. The roots were 3 plus I, 3 minus I, and be careful, what's the last root? There you go, you got it. Then it was a minus 1. Cool? Minus 1 would be the last root. So why did I want you guys to learn long division before? It was for this. Because what you just did is in that one division, what did you do? You divided out 2 things at the same time, didn't you? So did it kill 2 birds with 1 stone? Okay, here's the last thing. And I'm going a little bit off script. This is the one page, Kevin, I wish I had uploaded for you guys because this is a big polynomial. But it starts with 2x to the 5th, 13x to the 4th, 26x cubed, negative 13x squared, negative 18x, and 1/3. Okay, I'm not going to do the whole problem because for the sake of time, I'm just not going to. But I'll show you that this one works. And what I want to do is I want to show you a different way. And this is the coolest thing. This was something I actually was playing with myself years ago. And I'm like, I wonder if we can do this. And I was so happy to find out that the answer is yes. Because a lot of you guys like synthetic division, don't you? I think a lot of you guys are like, I'm a fan of synthetic division. This is a weird synthetic division now. Let me tell you, it's a weird synthetic division. So we're going to try that. So I'm going to blow right across this and write, so let's write -3 plus 2i. And I'm going to write all these coefficients. 2, 13, 26, -13, -18, and 130. Now, I'm only going to do 2 divisions, and you'll see why in a second, because we could execute the rest if we wanted to. But here comes the really, really important thing to do. Okay, take out your machine, because without this, this is not fun. But with your machine, it's a joke. I think I'm going to use my teacher's edition one here. Okay, here we go. Take -3 plus 2i. Now, if you didn't know that I was there, it is second decimal point. I is sitting on your calculator. -3 plus 2 second decimal point, and let's store that as alpha A, which I've shown you how to do before, right? Store alpha A. Now, let's help me go through synthetic division. What's the first step to synthetic division? You tell me what to do. What's the first thing? We bring down the 2. Now, what am I going to do? I'm going to multiply this by A. So times, so I have 2 times A, and that is -6 plus 4i, right? Now what do we do? Use your calculator. What are we going to do to this -6 plus 4i that's sitting there? We're going to add it to the 13 that's above it, right? So plus 13. Do not hit clear as you go. Keep that number sitting there. What am I going to do with that 7 plus 4i that I have? Multiply it by A times A. I got -29 plus 2i. Oh, now what? Plus 26. Okay, can you guys proceed? You know how to do synthetic division, so I'm going to do it while you do that. So I'm going to multiply that by A. And this is where we either smile or cry. What better happen on this last step? It better come out to be 0, because if it doesn't, it sucks. Times alpha A, and I got exactly -130. What did that show me? Did it work? Yay. Now, by the way, was that hard to do? Why is it easy? Because your calculator does it. If you don't have your calculator, don't go that way. But here's the cool thing, and then I'm going to stop. -3 minus 2i. Now, why do I know that one works? Because that was the conjugate roots theorem, right? You don't need your calculator anymore, by the way, because watch what happens. You drop the 2, and you get a -6 minus 4i. What just happened? What happens when you add down? Do you see it? What happens when I add down, everybody? Don't the i's disappear? And I'm down to 7 minus 6 is 1, and then I multiply again. What happened again? The i's go away, I get -6. I multiply again, I got 18 plus 12i. What do you know? The i's go away again. And then I come up here and I get -3 minus 20i. I screwed that up, that was a 20i. And that, do you see what happened? So the first step sucks, didn't it? It was kind of hard. But the second step is easy. So the question is, what's better, long division or this? Some of you guys are like, I like that. That's pretty easy because if I just hit buttons, it does it for me. But some other people actually like the other way better. And every year I have about 50-50. So could you have instead have done polynomial long division on that instead? Could you have done that? Will it give you exactly the same answer? I don't care which one you use. Pick one. What's the benefit of this? It's a twofer, isn't it? Don't you get two steps done at once? The benefit to this is your calculator does all the little picky details as you go. You just have to be really, really careful as you go. I don't care which one you like. So your assignment is in the textbook, so jump in there and get that thing going. It's 2.5. You're going to do number 3 to 30 by threes. Some of them are just going to say like, hey, is this a root? And you're just going to find out, did it work, okay? Sometimes it's going to ask you to list what they are, and you're going to factor it down. So the rest of the period is work time. I know it's not a lot. It's about just under 20 minutes, but I was trying to give you as much as I could. And I will be there. Let me go ahead and stop the recording.